A ship this large is almost impossible to comprehend until you see what is hidden inside it. The engine room alone is large enough for maintenance crews to walk through, and the engine drives a propeller nearly as tall as a 3-story building. But the real question is not simply how big this ship is. It is how engineers managed to build one, and how they managed to build an entire fleet of them. The vessel at the center of this story is the CMA CGM Jacques Saadé, the first in a series of 923 TEU container ships powered by liquefied natural gas, or LNG. At 400 meters long and 61 meters wide, it belongs to a class of ships built on a scale that pushes modern shipbuilding to its limits. To understand why ships like this matter, consider how the modern world moves, from food and electronics to machinery, clothing, automobiles, and industrial equipment. An enormous share of international trade travels by sea. The ships carrying that cargo are effectively moving pieces of the global economy from one continent to another. But shipbuilders have reached a practical limit. Make a vessel much larger, and its usefulness can actually decrease. Ports, waterways, canals, docks, and other infrastructure place physical limits on what a ship can carry and where it can go. So the competition is no longer simply about building the biggest ship imaginable. It is about making enormous ships more efficient. That was the challenge CMA CGM took on when it decided to build a new generation of ultra-large container ships powered by LNG rather than conventional marine fuel. The idea was ambitious. Build a ship roughly 4 football fields long. Give it a capacity of about 23,000 20-foot equivalent units. Equip it with an LNG propulsion system, and then repeat the entire process 9 times. The construction took place at the Jiangnan-Changxing shipyard in Shanghai, one of the world's major shipbuilding facilities. And a ship this large cannot simply be assembled like a car. It has to be built in enormous sections. Those sections are known as blocks. The process begins with steel. Thousands of steel plates are cut, shaped, reinforced, and prepared before they ever become part of the finished vessel. Instead of assembling everything inside the hull, engineers install many pipes, cables, fittings, and other systems inside the blocks while those sections are still accessible. That approach saves enormous amounts of time later. But it creates another problem. Every component has to end up in exactly the right place. Because once a block weighing hundreds of tons has been installed, correcting a mistake can become an enormous engineering operation. Some of these blocks are small enough to resemble sections of a building. Others are several stories tall, and some are so heavy that lifting them requires massive gantry cranes working together with extraordinary precision. One section of the ship's stern, for example, can weigh hundreds of tons. It has to be lifted, positioned, aligned, and joined to the rest of the structure with tolerances measured in millimeters. At this scale, a tiny mistake is no longer tiny. A few millimeters in the wrong place can create problems that spread through an entire system. Once the blocks are positioned, thousands of welds begin joining the ship together. The welding itself becomes a project on a monumental scale. Every seam has to withstand enormous forces. The finished vessel will spend years exposed to salt water, waves, vibration, temperature changes, and the constant stress of carrying massive amounts of cargo. So after welding comes inspection. Engineers examine the joints carefully, looking for weaknesses that could become dangerous once the ship is at sea. The hull may look complete from the outside, but some of the most difficult engineering work is still hidden inside because this ship is not powered by conventional marine fuel. It runs on LNG. Liquefied natural gas is natural gas cooled to approximately -161 degrees Celsius, allowing it to remain in liquid form and occupy far less space than the same gas would at normal atmospheric conditions. That creates a completely different engineering challenge. The fuel has to remain extremely cold. If heat enters the storage system, the LNG begins to warm and vaporize. So the fuel tank cannot simply be a giant metal container. It has to function more like a gigantic industrial thermos. The Jacques Saadé is equipped with an LNG tank holding about 18,600 cubic meters of fuel. That is an enormous volume to keep at cryogenic temperature inside a moving ship. The tank uses a sophisticated membrane containment system designed to isolate the extremely cold LNG from the warmer environment around it. And the details matter. The tank has to remain secure while the ship bends and flexes under the forces of the ocean. The containment system must also accommodate the physical effects of extreme temperature differences. That is why LNG tank construction requires specialized engineering rather than simply thicker steel. Before the tank can be accepted, its containment system must be carefully tested for leaks. Engineers inspect joints and connections, searching for even the smallest imperfection, because when the cargo inside is a cryogenic liquid at -161 degrees Celsius, a small leak is not an acceptable defect. The technology behind these tanks comes from GTT, a French engineering company specializing in membrane containment systems for liquefied gases. CMA CGM selected GTT for the design of the LNG tanks and associated technical services on this project. Once the tank is complete, attention turns to the machine that will consume all that fuel, the engine. And this is where the scale of the ship becomes difficult to imagine. The vessel uses a massive dual-fuel engine designed to operate on LNG. It is not simply a large version of an automobile engine. It is an industrial machine built around enormous cylinders, a huge crankshaft, and a propulsion system designed to move a vessel weighing hundreds of thousands of tons. The engine's crankshaft is one of its most critical components. Its job is to transform the movement of the pistons into rotational power and transmit that power toward the propeller. Installing a component of this size requires specialized transport equipment and extremely precise alignment. The crankshaft cannot simply be dropped into position. It has to be aligned with the rest of the propulsion system so that the forces generated by the engine can be transferred smoothly through the ship. At the other end of that system is the propeller, and the propeller is enormous. It is a single massive component designed to push an entire container ship through the ocean. But even something as seemingly simple as a propeller requires precision. The propeller shaft must align correctly with the propeller and the engine. Any significant misalignment can create vibration. And at the speeds and loads involved in marine propulsion, vibration is not merely an inconvenience. It can damage equipment, reduce efficiency, and eventually threaten the reliability of the entire propulsion system. Engineers therefore use specialized fitting and contact tests to determine exactly where mating surfaces touch and where adjustments are required. Only when the propulsion system is properly aligned can the engine's enormous power be transferred efficiently into the water. But building the hull and installing the machinery is only part of the challenge. The ocean itself is an enemy. Salt water is highly corrosive. Constant exposure to seawater, combined with mechanical friction and changing weather conditions, can gradually attack exposed steel. That means the ship needs a protective coating. Thousands of square meters of surface have to be prepared and painted, creating a barrier between the steel and the marine environment. The coating also has another purpose. A smoother hull can reduce resistance as the vessel moves through the water, helping improve efficiency. On a ship this large, even small improvements in resistance can matter, because the vessel will travel enormous distances during its operational life. Then comes one of the final major pieces of the structure, the command bridge. This is where the captain and crew control the vessel. From here, navigation systems, communications, propulsion, and the ship's surrounding environment come together. The Jacques Saadé also incorporates a system known as Smart Eye, which provides the bridge team with an enhanced view of the ship's surroundings and supports navigation with a bird's eye perspective and additional information. But before a vessel of this size can enter regular service, construction has to give way to testing. The ship must prove that every major system works. The engines have to be tested. Navigation systems have to be checked. Emergency systems have to be verified. The hull and internal systems have to be inspected. And the ship's anchoring equipment has to demonstrate that it can handle the forces expected during real operations. Only after the vessel has passed its sea trials can the engineering team finally begin to trust the enormous sea machine they have spent years creating. The Jacques Saadé officially joined the CMA CGM fleet in September 2020, becoming the first 23,000 TEU container vessel in the world powered by LNG. It was also the first vessel in a planned series of 9 ships of the same capacity and propulsion concept, and LNG was not chosen simply because it sounded futuristic. CMA CGM promoted the technology primarily for its impact on air pollutants. According to the company, LNG propulsion can reduce sulfur oxide emissions by about 99%, fine particles by about 99%, nitrogen oxides by roughly 85 to 92% depending on the comparison, and can reduce carbon dioxide emissions by up to around 20% compared with conventional fuel systems. That does not make LNG a zero-emission fuel. It is still a fossil fuel, but for CMA CGM, it represented a major step toward reducing the environmental impact of ultra-large ships, while alternative fuels and technologies continued to develop. And there was another engineering problem to solve. How do you refuel a ship of this size? The answer requires infrastructure just as impressive as the vessel itself. In November 2020, the Jacques Saadé became part of the largest LNG bunkering operation then carried out for a container ship. Its 600 cubic meter tank was refueled in Rotterdam, while normal port operations continued. Later, the vessel also became part of the development of LNG bunkering infrastructure in other major ports. This was essential because a ship designed to travel between Asia and Northern Europe needs reliable access to fuel along its operating network. The ship itself may be the visible part of the project, but behind it is an entire industrial ecosystem involving shipyards, engine manufacturers, cryogenic technology companies, classification organizations, fuel suppliers, port authorities, navigation specialists, and thousands of workers. That is what makes the construction of a vessel like this so remarkable. It is not one machine. It is thousands of technologies working together. And it is not one engineering discipline. It is naval architecture, metallurgy, welding, mechanical engineering, electrical systems, cryogenic engineering, software, logistics, propulsion, navigation, and countless other specialties converging inside a single moving structure. The result is a vessel 400 meters long and 61 meters wide, capable of carrying approximately 23,000 20-foot equivalent units and operating on LNG. In October 2020, the Jacques Saadé demonstrated just how much cargo that capacity could represent when it carried more than 20,700 full containers on a voyage from Singapore, setting a world record at the time for the number of full containers aboard a single vessel. And that was only the beginning. The original project called for 9 ships of this size. The names would include CMA CGM Jacques Saadé, CMA CGM Champs-Élysées, Palais Royal, Louvre, Rivoli, Montmartre, Concorde, Trocadero, and Sorbonne. Each one represented the same basic challenge: build an enormous floating structure, install a propulsion system powerful enough to move it, create a cryogenic fuel system capable of storing thousands of cubic meters of LNG, test every component, and then send the finished ship into one of the harshest environments on Earth. The ocean does not care how expensive a ship was to build. It does not care how advanced its technology is. Every weld, every valve, every sensor, every engine component, every section of the hull has to perform when the vessel is thousands of miles from land. That is why the construction of the Jacques Saadé is more than a story about a gigantic ship. It is a story about precision, a story about logistics, a story about thousands of people coordinating their work around a structure that is itself larger than many city blocks. And perhaps most importantly, it is a story about how the shipping industry is trying to solve a problem created by its own success. The world needs ships capable of moving enormous quantities of goods across oceans. But those ships also have to become more efficient and produce fewer harmful emissions. The Jacques Saadé represents one answer to that challenge. It is not the final answer, but it demonstrates what happens when engineers take an existing idea, push every part of it to an extraordinary scale, and then redesign the systems that make the whole thing possible. A steel structure 400 meters long, a cryogenic fuel tank holding thousands of cubic meters of LNG, a massive engine turning a giant propeller, thousands of components assembled with millimeter-level precision, and an entire fleet built around the same technological concept. From the outside, it looks like a giant container ship. But inside, it is something far more complex. It is a floating industrial system, engineered to carry a piece of the global economy across the planet. And every time one of these vessels leaves port, thousands of engineering decisions made years earlier are put to the ultimate test. Out on the open ocean, there is nowhere to hide from a mistake. The ship simply has to work. If you enjoyed this journey inside one of the most extraordinary ships ever built, make sure to subscribe to Nova Reports for more stories about the engineering, technology, and discoveries shaping our world. And if this massive LNG-powered container ship surprised you, let us know in the comments what you would like us to explore next. Thanks for watching, and we'll see you in the next documentary.